So let's apply this connection of G and K to an equation we've already looked at. The equation of carbon tetrachloride breaking into carbon and chlorine, we knew the delta H and S, and previously we calculated the value for delta G. It was positive. Positive means that it requires the input of free energy or reactants turning into products is not thermodynamically favorable. It asks us to solve for K, but before we even get the value of this, we can connect what it means to not be thermodynamically favorable. It means that this won't turn into those very much, or from an equilibrium sense, I'll have way more reactants than products, a small number over a much bigger number. When I rearrange my equation here to solve for K, I do E to the negative delta G. I change that to joules because this 8.314 is joules per mole Kelvin. So that the joules cancels with the joules. We've got the moles. We've got our kelvins to cancel here as well. And when we do all of that, we get an answer that makes sense. A K that is very, very small. We are greatly favoring our reactants. Right here on B, it shows us the Haber process. That is the reaction we looked at, nitrogen and hydrogen making ammonia. It gives us a value for K. So under standard conditions, K is very large. The products are favored. If I want to know how favored they are in terms of delta G, I need to change my K to a delta G value. I plug in negative 8.314, 298. The natural log of that value gives me my joules per mole, and I can change that to kilojoules per mole. It is negative. A big K matches with a negative delta G. The last thing here is much more common in terms of multiple choice or something that you would have to explain conceptually without necessarily doing the mathematical proof. We have a reaction of sulfur dioxide and oxygen to make sulfur trioxide. It told us that delta G was negative. That means it is thermodynamically favorable in the forward direction, or we have more products than reactants at equilibrium, which is why K is greater than 1. The next one, carbon monoxide and water vapor making carbon dioxide and hydrogen, has a K greater than 1. That means it's favorable. Nitrogen and oxygen making nitrogen monoxide requires free energy. Because it requires free energy, we have far less product than reactant at equilibrium, or our K is less than 1. And nitrogen or dinitrogen tetroxide turning into nitrogen dioxide has a small value of K. That means we're likely to have less products than reactants and have a positive delta G. So we can do this with equations, or we can just think of what the signs mean by connecting with the equations.